Well, is it really happening, guys? Welcome back to SkyTour Livestream. It is one of those nights where it's kind of on the border, but we have nice clear skies with some high clouds, so we're going to kind of skirt the clouds. I want to welcome you all back to SkyTour Livestream. I'm Marc Dantonio, your host for the evening, along with our wonderful co-host that we all know and love, Daryl Mason. Hey, Daryl, how's it going?
Well, Mark, I'm nominal, thank you. How are you? Hello, everybody.
I'm good, thank you. Tonight we started off with an old standby one that's beautiful. It's the Pleiades, and there we are. Now you'll notice there's some little fuzz around here. That's actually some of the high clouds, but not to worry. We're gonna, like I said, make our way around those. I want to say hello to everybody that has joined us early, okay, and give kudos to Donald Kunzer, who was the first one here. Hey, Donald, how are you? Good to see you. On Ahata 77, Bonnie is here with us. Nice to see you. And Michael Hedrick, what's going on, man? Nice to see you as well. Cyclone's with us. Daisy and Zoe Amethyst are with us. Fantasy's with us. It's so cool to see you. Michael Klagus, how are you, man? Good to see you. And we're going to just cruise on by. John G is with us. And we have a Drunken Photon. That's pretty cool. Hi there from a Wavy Particle. All right. Very good. And Izabela, of course, is with us. Hi, Izabela. So nice to see you. And sometime soon, Izabela has won a free night of... she's going to get an hour of time on the telescope to do whatever she wants. And she's creating a list. And she'll be checking it twice. And Daryl and I will certainly be naughty, not nice. Oh, well, you'll be nice. Okay. Yes, so that's great. So hello to PG, and hello to Robin Curtis, who is with us. Hi, Robin. How are you? And Robin's going to have some stuff to share with us at some future point. Some cool stuff that she's doing for us. And Papa Tom is with us. Carbon Star is with us. Carbon Stars are cool, and I like that name, Carbon Star. It's a very cool name because, to me, a carbon star is a really cool... anomaly in the universe. Carbon stars are supergiant red stars that are on the asymptotic giant branch, which is a second path up to red gianthood. And these stars dredge up carbon from their interiors and put it so far away from the central core that the carbon atoms can bond together and form carbon molecules, effectively soot. And these carbon stars become very red as a result. Very cool. Tim F. is with us. Hey, Tim. And as we get going here, I'm hoping, hello Sam S. and Marie Wilson, hello there, Maria Wilson, nice to see you. Guys, make sure you subscribe if you haven't yet, check us out, stick with us for a while, because we do some wonderful things, and I'm sure that the other people in the chat will tell you what's going on. And just to remind everybody what we're doing, okay, this left spot up here, this is the telescope controls up there. All right, so when I mention this area here, okay, this right here, this is our telescope control section. This is our telescope computer. This is the telescope, that wasn't right. This is the telescope in the building right here. Okay, this of course is the main screen. This right here is a stacking window. We're actually stacking dynamically all these. Every time it takes a picture. This is the camera control cluster over here, and over here in the camera control cluster, the very most important things to look at are this guy right here. This is the exposure time. That's important. All right. And then we have the gain, which is right here. The gain tells us how sensitive the computer or the camera will be to get our imagery. Okay, so let's wipe all that out. Now that you've had the basic introduction, we can now keep going. So that's what you'll see. Now, many times what we'll do is we will, in fact, do this. We will enlarge our screen here and bring our objects front and center and enlarge them in the window so you can watch what's going on. It doesn't hurt them. We will just see them coming up in here bigger and bigger. So this is the Pleiades, all right? Something that we have seen many times before. And the Pleiades looks beautiful tonight in spite of the clouds. This dust right here is the dust that the Pleiades stars happen to be embedded within. and Daryl and I have talked about this before. These particular stars are in a dust cloud that may very well extend to our solar system and beyond. It happens to be because the stars are not all that far away from us. They're just several hundred light years from us, and so that sounds like a huge distance, but it really isn't in the grand scheme of the universe and so forth. This dust, these stars happen to be passing through it, and the Pleiades are not just these stars here. Okay, there's over 100 stars in the Pleiades cluster, and we're seeing some of them here as we back out a little bit. These are a lot of the stars in this cluster. These happen to be some of the brighter ones, and they're passing through this dust. And as they're passing through this dust, they're, of course, emitting starlight, and the starlight's being scattered by these tiny particles of dust. Little factoid: the effectiveness of the spectral scattering, in this case the blue light, tells us a little bit about how big the particles are. Okay, and that's something that's very important to us as astronomers. We want to figure all this out. All right, now we know that the Pleiades and this dust cloud are not together and running together and through space and going around the galaxy, because the dust is going one way and the stars are going another. So they're just passing through. Kind of cool, really neat. Let me bring my telescope back here. Marianne is here. Yes, that's right. Hi, Marianne.
Hello, Marianne.
Get back. There we go. Okay. Yeah. And Marianne says, happy 2023, everyone. Finally, first stream of the new year. Yeah, it's going to be an amazing year. And she has a reason to say that, because for those that may or may not know, SkyTour LiveStream, our observatory systems, have just become a legal 501c3 not-for-profit corporation. So we are going to be looking to be supported by folks like you and by people that are, interested in astronomy in a very serious manner. So that is something that we're looking forward to. We have a Patreon, and if you go here to skytourlive.com, right down there, okay, or skytourlive.org. I'm going to change that, because now that we're a 501c3, skytourlive.org is probably better to talk about. Skytourlive.org is our portal that will take you to SkyTour Livestream here, takes you to SkyTour Radio, our radio show. It takes you to our Patreon. It takes you to a gallery. It takes you to some bio information, tell you all about us and where we came from. And so you'll have fun with that. So let me know if you have any questions about that. We're here all night. Well, for a couple hours anyway, right? Oh, Izabela just put up our Patreon. Thank you, Izabela. She just put the link up. Thank you very much. And we have a Twitter as well. And if you go to skytourlive.com, you can click on our Twitter link as well down below. So we have Instagram, Twitter, Facebook, and all those things. So it's pretty cool. And Bonnie says you missed her previous greeting there, Daryl. Yeah. So, now that we get all that out of the way, let's go check out the night sky with our AllSky camera. That's the one other thing that we have, and this is our AllSky. You can see the stars. This time I took this shot, there was a satellite coming through. This is some bird doo-doo that was on there that the rain that had occurred previously washed off. I'm just going to do 1 second shot here. Now this looks like a bright sky, but it's actually a very dark sky. Okay, this is the western horizon, so it still has where the sun was. Okay, and as you can see, it's now gone. This glow here, this is from Phoenix, which is 65 miles away to the east. Okay, so this is east, this is west, this is north, and this is south. Here you can see Orion, and just to give you just a little more, just a little bit more of a idea. Okay, so here is Orion right there. Okay, we have Betelgeuse, we have Bellatrix, we have Rigel, and we have Safe. And these are the three belt stars in Orion right here: Alnitak, Alnilam, and Mintaka. And right there, that little fuzzy spot there that we're going to see later, That's the Orion Nebula in the Sword of Orion. Now, where we're looking right now is in the Pleiades. And can you see the Pleiades on our screen right here? Maybe not as easily. But, okay, if you look, right, the Pleiades are pretty high up. But I believe these are the Pleiades right here.
Yes.
And then we have Aldebaran and the Hyades right there. Right?
Mars.
And Mars is up there, right there. Okay, that's Mars. Let me,
Mars right there.
Yep.
It's Capella higher up.
Right, this is Mars right here. And this is Riga and Capella and the kids. We just need to go a little further. But that's another place we may spend some time tonight, is going through Riga. And here you can see the winter Milky Way. And then right here, okay, this is Cassiopeia. Let me see if I can actually trace it for you. And this goes here, there. Oops, I missed it. It goes there. So right there. I screwed it up.
More or less.
Yeah, I know. I messed up with my my mouse. It got let go. So do this, and this. There we go. There's a W of Cassiopeia. All right. And so Cassiopeia has some really cool nebulae in there. There's one right there near the star Navi, which is neat. You see our clouds here. Those are, if they're here, they're luckily they're kind of away from us, but they may intrude as the night wears on. But as we're waiting, we're still photographing the Pleiades. So let me minimize this AllSky cam. And when I minimize that cam, you'll see the Pleiades still being taken here. And they're just beautiful. There we go. And you'll notice that they have some little halos around them. That's because they're so bright that our system runs at a very, very fast speed. So photographically, so in this arena, our telescope is running 25 times faster than when we purchased it. So we'll get halos. But here's the dust. This is all very real dust.
Cyclone has a question for you.
All right. Question: what is the furthest constellation that is from Earth? That's actually interesting question. I don't know the distances to the furthest stars in many of these constellations, but they got to keep in mind that the constellations have stars that are at all different distances from us. Give you an example. Okay, we go to Orion. Okay, Betelgeuse is 750 light years from us, but Alnitak, Alnilam, and Mitaka in the belt are actually over 1,000 light years from us. Okay, the Orion Nebula is 1,500 light years from us. So it's all 3D. So it's hard to answer that question because they're made up of stars that are somewhat close to us and some that are far. Aldebaran and the Hyades. Okay, the Hyades are not the same distance as Aldebaran. Aldebaran is closer to us than the Hyades. So it works that way. Now these stars here we're looking at are about 400 light years away. But some are closer than others, but by several light years, several tens of light years. But by and large, they occupy the same little sphere of space, you know. Anyway, but that's a great question. But thank you there, Cyclone, for asking that question. All right. So, in terms of what we're doing here, this is the Pleiades, and I'm going to just throw it out there for you to see. And it's called an open cluster, right? And we abbreviate that OC, all right? So let me fling that out there for you. There you go.
I saw an interesting graphic a day or two ago. It was showing the Milky Way galaxy, looking down on it, and there was a tiny little yellow circle drawn inside part of it, and
Okay.
that showed all the stars that we could see from Earth are inside that little bitty yellow circle. Relating to what Cyclone asked, I had to think about it for a second, but I would guess Orion maybe as much as any constellation. As you said, you know, the stars are close, stars are far away, but on average, maybe Orion might not be a bad guess.
Yeah. Very cool. So these are the seven sisters. You might recognize the symbol from the Subaru automobile. They chose these stars because these stars in the sky represent unity, because they are all moving together through space. All right. The dust isn't, but they are. And so because they're unified in their mission around the galaxy, they chose the word that means unity for their logo. And there's various translations of it, you know. Okay, let me, I can pull the object ID out there because we know what it is now. Yeah. So when we look here, this is Alcyone right here. This is Atlas and, why am I drawing a blank? What's the other one? Atlas and the daughter... Pleione, hello. It was Atlas and Pleione, and this is Merope.
They're the parents of the seven sisters.
Okay, yeah. So Atlas and Pleione are the parents right here in mythology. Alcyone is this star right here, and it looks like it has several other components with it. I don't know if those are actually part of the same star system. They're probably at various distances from us, but still interesting. This is Merope, and this beautiful nebula here is called the Merope Nebula. Okay, this star here, I'll come back to that. This is Maya, and you see this little swoop right there, this little blue edge. That's the Maya Nebula right there. Is this Tegeta?
I never can keep them all straight.
We gotta try and keep them straight. Let's go in for a minute to our trusty, dusty thing here. Okay. Merope, Electra. Okay, yeah, okay, good. All right. So, I got them almost all right. You know, we did okay, Daryl. We did all right. So, basically, this here is Electra, all right? And Electra is here next to Maya, and this star is Tegeta, or Tegeta. I mean, I'm not sure how to pronounce it.
Tegeta.
Is it Tegeta or Tegeta? Yeah. All right, well, there you go. So that's the Pleiades of the seven sisters that we know. But again, all these other stars, and many of these other stars here that we're looking at, are also part of this overall cluster. It's just these are the attention hogs.
Kathy, that's an interesting question. That's debatable because those are all very hot blue stars.
Oh, yes. Did Kathy ask about planets?
Yeah, are there any planets associated with stars in the Pleiades?
Oh. Well, I will say this. The B stars, O stars, the answer is probably no. B stars, the answer is likely no. And it has to do with the fact that these stars have such high amounts of ultraviolet radiation when they're first born, and they last a few tens of millions of years if they're O stars, and for B stars, a slightly longer. But the thing is, these stars have such ultraviolet radiation that it would actually sterilize any planet. It would probably strip off atmospheres forming on some planets. However, I do believe there's at least one exoplanet that was found around a B star. It's a very hot Jupiter-type B star. A planet around this B star, and it may be that star is slowly eroding the atmosphere of that planet, right? But when you get to A stars, because it goes O, B, A, F, G, K, M, and the M stars are the coolest and the smallest and the most plentiful in the entire universe. And the M stars are also the ones where most planets are found. Because of the most copious copious star in the universe, it stands to reason that most of the planets we know of are around those types of stars. Our star is a G star, so it's the very, very hot and blue O, B stars, the white stars A, the slightly less white stars, F heading toward the yellow, the G stars more toward the yellow, and then the the K stars, and then the M stars, so O, B, A, F, G, K, M, and it goes down in temperature from there. The correlation showing how those stars actually work was created and discovered by Ejnar Hertzsprung and Henry Norris Russell, and that became known as the Hertzsprung-Russell diagram, or the HR diagram. And when we plot those stars that are just are fusing hydrogen into helium normally, they form a line from the upper left to the lower right. Nice line, and we call it the main sequence. Giant stars end up off those, up above the main sequence, because they're no longer doing hydrogen to helium, they're doing helium into carbon, carbon into other things, all the way to iron. And that's really, really something. So there you go. So I think we're done with the Pleiades for now. And I started this exposure long before I actually had you guys come on. So I'm going to pause this stack here. And then up here, I'm going to type in what we're taking a picture of. It's the Pleiades, Pleiades. And why am I doing that? Because when I save this stack, it goes to a place where you can see it in seconds. And just like this. And so now it says it was saved to this particular directory. And I have it set up so that all the files saved to these directories, right? And this is the ping file, the image. Go up to our server. The server is fully available to you. You can find it by going to SkyTourLive.com, or someone like Izabela will put it in the chat, or Daryl. They both.
Yeah, she posted it a minute ago.
All right, see that ahead of me.
I'll try to post it in here.
And so, what will happen is, I just save the stack in the raw image file format called FITS, F-I-T-S. It's an astronomical format we use in astronomy. And that's not all that useful to you unless you're going to process them in Photoshop on your own, which is fine. We encourage it. We teach people how to do it, in fact. But the ping file that we save is an image file that is exactly what you see here on the screen. Okay, it's exactly this. And if you want to take this and use it, put it on your desktop, do whatever you want, more than happy to let you do that. Okay, and when my invisibility potion wears off, I'll come back, and there we go. We're coming back slowly but surely. There we are. Okay, so and within about 30 seconds, these files will be up on the server, and you can go check out exactly this photo we just took and enjoy it. All right. Now, if you join the Patreon, then you get the results after I process these and get rid of all the halos here and make these look just beautiful and make them very big, so you can put them on either giant posters, or you can put them on wall hangings. I actually have in here stretched canvas images. I also have what's called a wall decal. And the wall decal is this weird thing. It has a backing. It's a photograph, but then it just goes on the wall. Flink! And like a picture. Just like that. Done. And you can take it from there and move it over somewhere else if you want to. It's pretty cool. And you can get those at 20 by 30 size or so. So that's pretty cool. You know. Hello to Simon. How you doing? Nice to see you. Sam S. says, Marianne, I received an email this evening from Amazon that they are discontinuing the Amazon Smile in February. We'll check that out, because we do Amazon Smile as well. And Daryl, thank you for the address there, putting the link in. Yeah. Okay, so now that we have this, we're going to get rid of this stack because we already saved everything. Nothing is now, we're going to dock it up again there. Nothing is lost, and what we'll do is we'll go back to our 1 second, and we go to something I call our night vision mode. Okay, and that is this mode right here. So this is a night vision mode where we actually see the stars using our system in this night vision mode, and it helps us to visualize. You can even see the little nebulae in there and everything. And now we go to our planetarium system. It's linked to our telescope. And we'll back out. Marianne, check on that to make sure Sam is saying that this is not a particular piece of Amazon Smile, but all of it. I don't know why they would do that. Maybe it's just losing money. Okay. So I know you'll want to say, well, go look at the planets. Well, this is a wide field scope. Let me show you the actual view. Okay, we're at 34% on our frame, but let's go and let's auto size it. I want to just show you. Okay, so from here to here is 4 full moons across, and from here to here is 3 full moons tall. So planets are tiny little dots like these stars, and so Jupiter might be a little bigger, all right, but we can't see exactly what's on the surface of the planets with a wide field telescope like this. We need a higher focal length system, and just in time we are getting a higher focal length system. We're actually adding another telescope at possibly another location, and we're going to be able to do both of these side by side. Basically, you're going to see a wide field view and a close-up view of the objects that we're taking, and it's going to be beautiful. And Michael has a question. That's a Starlink satellite right there. We're using Starlink, by the way. Our observatory is green, meaning that we use the energy of the sun. We're not on the grid, and so we have green energy for everything in there, and for all the cameras, the telescopes, all that stuff. All right, and so we use Starlink for the internet. So we're in the middle of nowhere, out in the middle of the Arizona desert. All right, so Michael, I asked if he had a question. I said, and Daryl said, post it. January 18th, Mercury stationary and Pluto in conjunction with the Sun is on my astronomy calendar. Okay. Well, you want to take that one, Daryl, or would you want me to?
Sure. Mercury stationary, I'd have to look it up. Mercury recently passed from the evening sky. It was above Venus, and it turned the corner in its orbit and dropped like a rock, and it's now on the morning side of the sun. It's west of the sun, that is.
Yep.
And if Mercury is stationary, that means it's about to turn the corner on the far side of its orbit again, which sounds almost too soon to me. I'd have to look it up in a planetarium program. But that generally Mercury is stationary. Any planet is stationary when it is, you could say it's turning the corner in its orbit around the sun as seen from the planet Earth. Pluto in conjunction with the sun means it's in the same part of the sky as the sun. It's basically as close to the sun from our point of view as it's going to get. And once it's closest in conjunction, you might remember Saturn and Jupiter were in conjunction over in the southwestern sky after sunset a couple of years ago. Made a very pretty view. That just means that they're as close to each other from our point of view in the sky as they can get. And then they'll start separating again. Speaking of conjunctions, though, Saturn is going to be in conjunction with Venus here in the coming days. Saturn is dropping like a rock now in the western sky after sunset. It follows that line in the plane of the ecliptic that the planets move in and the sun moves in across the sky. Saturn is growing closer to Venus night by night. And here, I'd have to look it up some days from now. I have it written down somewhere. Give me just a second here.
All right.
Now I need to put my glasses on. Hang on.
Glasses? I have
glasses.
I can see without my glasses, but when I put on my glasses to see distance. So
yeah, Saturn and Venus are in conjunction on January the 22nd.
Okay.
4 days from now. And it'll make a pretty sight. Venus is so much brighter than Saturn, though, that Saturn will be relatively hard to see compared to Venus in the post-sunset sky.
Yeah.
Conjunction, as a general thing, just means when two objects come close to each other in the sky from Earth's point of view. Not that they're actually close to each other, because they're not. I mean, if you go out and you look on the 22nd, weather permitting, and you can see Venus and Saturn together in the sky. Well, Venus is rising. It's coming around from the far side of the sun, but Venus is much closer to us than Saturn is. When we see Venus now, it's maybe on the order of 150, 200 million miles away, something like that. But when we see Saturn, it's like 1 billion miles away. So much, much farther away. Just they're in the same line of sight.
Thank you, Daryl.
Yeah.
And while he was explaining that, I drove us to the Crab Nebula, which in the sky is right between the horns of Taurus the Bull, and that's right here. Okay, just about. Okay, and I'll just show you when I show you this. Right, it's sort of like the tip of one of the horns. So these are the horns of Taurus the Bull, and the Crab Nebula is in between them, but nearest this one. All right. So the Elnath? No, Elnath's up there. Yeah. Okay. No problem. All right. So we are currently at the nebula that is the remnant of a star that blew itself to kingdom come. Got destroyed itself. This is the Crab Nebula. Right there. And it's a supernova remnant. Let's check it out. This exposure, we're going to do 35 seconds, right? And we're going to stack it. This is going to show you something amazing. You're going to see a lot of detail in this nebula. And when I say we're stacking, what does that mean? It means that we're going to do this. We're going to bring this stack up, all right? And we're going to clear the previous stack, all right? And the stack is, we're taking a picture. Then we take a second picture. And we align them and stack them on top of each other. And we do it automatically. We make an image sandwich. Why do we do that? Because all the noise that we see in the imagery, all the noise from the electronic noise of the camera and so forth, is getting averaged out. And the images just get better and better and better looking. So here's an example. If we zoom in, you're going to see that it has some noise. I mean, it looks really nice, okay? But you notice that it's not that clear, right? It's got some junk in it, right? And I think we're going to refocus too, because I notice we're off on our focus a little bit. But I'll let this image come in just so you can see how much of this noise goes away with just the next image that gets slapped on top of it. Ready? Watch this. Here we go. Look at that. Now the detail starts to come out better. And I can see that, again, we're going to need to refocus. So we'll just get rid of the stack for a minute and go back to our night vision mode, which is quick and easy to do. All right. And then I'm going to go and do the auto focus system, which I think is kind of cool. When you watch this, you'll see what we do. What happens is the temperature out there dropped, and I forgot to apply our temperature compensation. I only just put it on. So without temperature compensation, we didn't actually manage to get the focus following the change in temperature, because as the temperature goes down, the focus does change. All right. So let's just get this out here. All right, let me
It's cold out there at night too.
yeah, the temperature is 9.6 degrees Celsius in there right now. Oh, here we go. All right. Now let's do this. Okay. All right, now you see the donuts. This is what happens when you have a defocused system like ours. We have a secondary obstruction, and that secondary obstruction is actually a mirror, not a mirror, a lens system leading into the camera. Our camera is sticking off the front of this telescope. So we're going to do this focusing, and as it gets focused, I'll just pull out for a minute, go to this mode here, so you can see how many stars are being used to perfect the focus. And then right here, we're going to build a curve, a parabola, and that's the curve of focus. So it's out of focus, getting more in focus, more in focus, more in focus, and it'll reach the bottom of the curve and then go back out of focus. And where it goes to the bottom and comes back up, the system will detect that that's the perfect focus, put a line, and that's going to be the best focus point that we'll go back to. And then our system will be critically focused, which is all you really want. Hello, Ricardo. I saw you before and I forgot to say hi. I apologize. How you doing? I know you guys. I know you hang out and lurk. That's okay. So many people do. It's fun. Look, it went up now, so there it is. So our curve now. All right, our curve now. You can see it. So this right here is our focus. Right there. There's our curve. Right, our focus point, the best focus is right here. So how do we get there? Well, that's easy. What we do is we just tell it to move to the best focus point. And now the focuser is going to be moved back, go through the entire roll, and then come back to that central spot. Now when we take this picture, it's going to be even more stunning. So we can get out of the focus now, come back in, and get ready to see some beautiful imagery. I like how the nights turned out, Daryl. It's not that bad after all.
Yeah.
Okay, this will be, again, this is a 35-second shot. No, I'm going to do this for 25 seconds. This doesn't require that much time. All right, now we're going to drop out of night vision mode and go into stack mode. And now we'll be in stack mode. That's the previous shot. See how the stars are a little fuzzy? Okay, in just a few seconds, I'm going to overlay this, all right? So we'll clear it now, and now watch. You're going to see a much sharper image here. Hey, Dean Bostador, how are you? Okay, here we go. Now look, we got a satellite go right through the Crab Nebula. That's okay. That satellite will disappear, but look how sharp the stars are now. Okay, let's color correct. All right. Let me clear it. No, it'll take a while. As they average out, as they stack, those satellite trails go away. But just by clearing it, it goes away anyway. Okay.
It's getting harder and harder to avoid those darn things. So.
I know it. It's a mixed blessing.
One day we'll be looking back and saying these were the good old days.
Maybe. Unless we actually start a program with satellites. Okay, now watch this noise, guys. It's going to get less. Look at that. See how much noise went away? Look at the filaments in this. These filaments, you'll notice the different colors. Okay, it's got green. That's oxygen 3, meaning O, and then Roman numeral 3, I. That's doubly ionized oxygen. All right, and the red is hydrogen alpha, or H2. That's H with a II, the Roman numerals 1. And that's singly ionized hydrogen. You can't have doubly ionized hydrogen because it only has one electron to ionize. So that's pretty interesting. Now, as we go here, we've got 3 stacked right now. And we're getting to the point where we can start to zoom in a little more on this. And I'm going to show you. Yeah?
Mark, Izabela, and Ricardo say I'm soft on the mic. I can raise my level, or you can if you'd rather.
I just raised you.
Okay.
But your level's kind of low. I can see that now when you're talking. So why not raise it up?
Okay. I did a little bit.
A little more. I know, but it is what it is. Wait a minute.
Well,
Let me hear you talk now.
testing.
All
1, 2,
right.
3, testing.
That looks a little better, I think.
All right, I can adjust my microphone also.
You're all right. Hey, dude. Dean asks, how long of an exposure is this? Right up here, Dean, you can see the exposure time. Let me point that out to you. Okay, right here you see our exposure box. This box will always be visible to you, and it tells you what the exposure is on our shot. This particular shot is 25 seconds. All right, and it's at a gain, that is a sensitivity, all right, that is here. And this gain that we're looking at right here is 300, all right? So, but there it is. It's always going to be up in, it's always going to be visible on the screen up there on the right. All right.
The moon is down tonight. Why are you at 25 seconds?
It's the Crab Nebula.
Yeah.
The center will be blown out. The center will be blow out. I'll blow out the center. Look at them. See what I'm showing right there.
Yes, I see. Carry on. I see the.
You got it.
Star.
Yeah. This the reason, and Daryl is correct. I am running 25 seconds. Normally I can go longer. But what I'm going to show you now is this. I'm going to modify this a little bit, and this beautiful filamentary structure belies what created it, and it was a regular. Red supergiant at one point, and then it exploded, and when it blew up, all this stuff was the guts of the star. All right, and you see these beautiful filaments, and this nebula has been studied for over 100 years, and there are time-lapse images of this thing expanding, okay, because it is expanding out. Hello, Ronald. Earth Radio is with us, and this one dot right here, okay, the dot we're talking about is this guy right here. Okay, you see that guy inside that square? That dot is what's called a pulsar. Now, a pulsar is a stellar remnant, a remnant of a star that went supernova. It's also a neutron star, as Daryl pointed out. A neutron star is a star that has been so compressed that all of the surface material are neutrons. All right? And how that happens is a class in itself. We could talk about stellar evolution at one point if you want to, and I can go through how neutron stars happen and how they change over time and how white dwarfs happen, etc., which are very different. But if there's a hot spot on the surface of a neutron star, which is rotating very, very fast, whenever you blow something up like a star, that core starts to really spin. And when it spins, sometimes there's a hot spot, and that hot spot can act like a lighthouse beacon, sweeping us, as it goes by. And we might see this in light or in radio waves. In this case, we can see it in radio waves, and we can see it in light. And you actually can see every 30th of a second, 33rd of a second, this thing is rotating. It spins 33 times a second. Okay? And so that, you might say, that's pretty fast, but it's not the granddaddy of these guys. The pulsar maximum is over 715, I believe, times per second that the star rotates around. 715 times a second.
Yep, that's getting into what's called millisecond pulsars.
That's exactly right, as Daryl just said. And the thing that's interesting about those, any pulsar, is that you would say, if it's spinning that fast, how come it doesn't fly apart? And that's because it is so compact, it has so much mass in its core, in its center, and throughout, that it's held together by this particular this gravitational pull that it has. And it won't collapse any further. Now, a neutron star could collapse further to a black hole if it was more massive. But there's a special pressure that the neutrons are resisting that compression with, being compressed even more. And that's called neutron degeneracy pressure. And so that's why the neutron star doesn't shrink any more than it does. White dwarfs, which are less massive objects, white dwarfs have electron degeneracy pressure. Again, just imagine a checkerboard in which you put an electron in every single square, and no two electrons can occupy the same square. So you fill the checkerboard with all neutrons, or electrons or neutrons, and you can't press them anymore. That's the way to think about this pressure that the star is pushing back with to keep from being compressed by its own gravity. And that's what holds the star up.
By comparison, like when we look at a white dwarf, say inside the Helix Nebula, the planetary nebula, we see a white dwarf in the middle. They often say it might be comparable to the size of Earth. That we took something the size of a star and crammed it down until it's the size of the Earth.
Right.
When we look at a neutron star like this, a general comparison I've heard is we've compressed it down to the size of Manhattan Island, and yet it's so bright that we can still see it.
That's right.
It's putting out very energetic radiation, which is what's illuminating the nebula.
Exactly. That's exactly right.
I read the other day about a special case of neutron stars that sometimes, and they're looking into this with the gravitational detectors like LIGO and the Virgo now.
Yeah.
There are special cases of neutron stars colliding, and when they collide, their spin is so fast that their spin is the only thing keeping the neutron star, the new neutron star, from collapsing into a black hole. Ultimately, gravity will win, and the star will collapse to a black hole. But there are cases where it gets so spun up when the two neutron stars collide, it's spinning so fast that it delays the collapse to black hole state. And the most extreme case I think they mentioned was about the neutron star survived for about a day before it finally collapsed into a black hole. And this is the most extreme instance of matter that we know of, still on this side of being a black hole.
That's right. And neutron stars can be anywhere from 2 to 2.4 times the mass of our sun. And beyond that, and remember what we're talking about now. We're talking not about the mass of the stuff out here. That went into making the mass of the original progenitor star, or the star that caused this. We're talking about the mass that's trapped in the core of the star that has collapsed. And now that is the type of mass we're talking about. And so 2 to 2.4 times the mass of the sun trapped in a core of stars, of that star, is a massive amount of material. And so that's why this is so important to study. All right, so let's back out of this now. And we'll leave it at several thousand light years away, too, which is kind of neat.
Michael, what would you like to know? He wants to know more about spin dynamics.
Okay.
If you frequent the APOD site, the Astrophoto of the Day NASA puts out, they re-released just the other day the classic Hubble image of the Crab Nebula here. And we've all probably seen it before, but boy, it's a stunning image. And it is just so incredibly complex. It's amazing to see. It's just mind-blowing how many filaments and how much stuff is actually going on inside the Crab Nebula.
Agreed. It is just an amazing location.
Yeah.
Okay.
And
well,
this was the very first object that Messier discovered.
Oh, that's right. That's why it's Messier 1. Yeah.
Yep.
Now I'm going to do one other thing here that we'll leave on. And as I zoom in here, you can see that central star. I'm going to add an unsharp mask. This is an enhancement to help sharpen things up. And now you can see it even better, and you can see the filaments even better. So this is a really cool addition. It's a neat way to to visualize things.
Izabela, I'm turned up quite a bit, and Mark increased my sound also.
I did. You're actually up pretty high, Daryl.
Okay, they say I'm still low.
Okay.
Michael, for your question, it's conservation of angular momentum. If you've ever watched, the classic example is a figure skater when she spins and does a pirouette. Well, she lets her arms out at her sides as she slows down, and then she pulls her arms in close and compresses herself along her vertical axis, that she spins up greatly and spins much faster. The same thing happens with a neutron star. Is the more that progenitor star, the faster it was spinning when it collapses and becomes a neutron star, or say you had two neutron stars collide and contribute their spin to each other, they're compressing so much that conservation of angular momentum says it's got to spin faster to maintain that angular momentum.
That's
and
right.
Thus you get like millisecond pulsars.
And that's what Daryl, what you just said, is very important too. Again, use the ice skater analogy. When they spin with their arms out, they're going just nice and gentle, but then they close them in and they start spinning much faster. Now, they're not spinning themselves faster. The conservation of angular momentum is causing them to spin faster. And so that spin is something that will occur with stars. And remember, as the stars collapse, any spin they have is going to increase and increase and increase. And that's why they can spin, as Daryl said, so fast that they can go around hundreds of times in a second. Very cool.
Okay, folks, I'm almost eating my microphone, so I'll try. I don't think I need to or should raise my level anymore.
Well, if they say you're still quiet, then maybe you should. I got you up as much as possible. Let me try one other thing, Daryl.
Yeah.
Let me try one other thing. Keep talking.
My settings are much higher than normal.
All right, keep talking.
Testing. 1, 2, 3. Testing.
Okay.
The quick red fox jumped over the lazy brown dog.
Yeah, I'm not able to. I'm not getting in. I'm not getting you up anymore. I'm just able to make mine go higher.
Yeah, I'm too high now.
Well, not really.
Well.
On the output here, you're still below me.
Okay.
Well, just make a directed effort to talk into the mic, and we'll figure it out at another time. Because
like
we have.
I said, I'm almost eating my microphone right now. It's very close to my mouth.
Well, I'm sure.
Well, let's try that. Carry on.
All right. Dew says, Mark, did you hear about the new theory that we are in a black hole now? Been there since the beginning of the solar system start? Well, it's kind of funny because I mentioned that the other night on the Clyde Lewis show. I think it was a Clyde Lewis show. Or did I say that on our show, Daryl? I think I might have said it on our show about being in a black hole.
Oh, I've talked about that before in the past.
Yeah. So we both talked about it.
Black holes, they think, you pass the event horizon and you get spaghettified and you're torn into constituent atoms, but it depends on the black hole. The bigger the black hole, you cross that event horizon and you don't necessarily get spaghettified. It depends on, it's sort of a reverse relationship. The smaller the black hole, the worse spaghettification is. Really big black holes, the event horizon is far enough away from the singularity at the center that the gradient, the gravitational, the tidal gradient is so shallow that you would survive crossing the event horizon. And somebody actually figured this out a long time ago. They supposed the mass of the universe. They took that mass and crunched the numbers, and it turned out that if we had a black hole the size of all the mass in the universe, it would be just about the size of the universe, and we are inside the event horizon right now.
Yeah,
That's kind of silly, but
well, it isn't. It isn't. I mean, because if you look at the black hole that is in the middle of Messier 87 in the Virgo cluster, right? That black hole is the size of our solar system times 5. You know, so that's a massive black hole. You know,
there are much larger ones than that.
Yeah.
I can't think of its name now. There's one they've been saying recently is the biggest one, and its accretion disk is bigger than our entire Milky Way galaxy. And there's been a new, supposedly really, really big black hole I've seen in just the last few days in the literature. It is like 34 billion times the mass of our sun. But that's nothing compared to, we took everything in the universe and crammed it into a black hole.
That's right. There goes a Starlink. Yeah, okay. Yeehaw. Okay, we're going to go to this little cluster because it's a very cool cluster to look at. And we'll check it out. And then we'll move. See, we're just biding our time until we can get into Orion more properly. And that's coming up soon. So let's go to this cluster. It's called the Shoebuckle Cluster, also known as Messier 35. It is a beautiful cluster that many people with telescopes go to when they look at their first object and it's winter. They might go to the Orion Nebula and Messier 35. And so this is Messier 35 right here. Messier 35 is surrounded by another cluster right there. And let's just go back to remind ourselves what that one was. Okay, because that one, let's see. Trying to bring up our, there we are. We'll zoom in on this. Okay, there we go. Okay, now let me have a delay here with Starlink right now, so it'll come back. All right, it's NGC 2158. Now, this red square represents the field of view of our telescope. You see it's on an angle. Where the words are, the letters, the numbers, you have to turn your head to the left, and you can see it just like you see it in our eyepiece, okay? So, 2158, right? Okay, 2158 is right next to it, right here. And this is Messier 35. Let's do a 25-second shot. We can go, because it's a cluster. It doesn't require a lot of time.
I remember this.
Right? Remember we talked about this?
Last time we streamed, or time before that, there's Messier 35 and then the little NGC object to its lower right.
2158.
Yeah, 2158. It's much farther away than M35.
Yeah, and it's reddened. You can actually see that. So now we go and we'll now do our live stack process we just talked about again. There's our Crab Nebula buffer from the last, and we're going to clear that. It's up on the server now. You can go check it out and enjoy it. And so you're going to see Messier 35 here in just a second with the slightly more reddened NGC 2158 to its lower right. Hey, Luid Rodriguez, how are you? Nice to see you. Thank you for joining us tonight. And the telescope will be able to spot the comet with no problem. We're going to see it as soon as it gets near Polaris, near the end of the month.
Yeah, it's up well before midnight now, but it's still
Low.
going to be below the north wall of the observatory
Yeah.
for some time.
Yeah. There we go. Look at that. So Measure 35 is beautiful. It looks stunning. And let's zoom that out there so you can see what it is. It's Measure 35, an open cluster, and that's NGC, again, 2158 in there as well. Beautiful. And little satellite trail right here that came through. All right. So that is a beautiful cluster. Yeah. I forget how many elements are in Measure 35. I think there's is it a couple hundred?
I don't remember offhand.
Well, it's about 2,700 light years away, and it's a rich cluster, meaning there's an awful lot of members in this cluster. Yeah. Look at that. That's just beautiful. And we have stacked 4 of them so far. And we're going to go just a couple more. Before we do that, I want to do one thing. I want to check out... I want to check out 2158. And get its distance. If I recall, I don't remember them giving us a distance for this one. Yeah, we get a parallax angle, you know, and that's it has more than 100 stars in it, and Measure 35 is also has about 100 stars in it. So these are both pretty rich clusters. We could use the redshift they give and calculate a distance, but it's all right. It's okay. Okay, this is 6 stacks so far. And as you can see, when we zoom in, it looks really pretty. Of course, look at that. It's like a jewel box, isn't it? It's like a beautiful jewel box of stars. And NGC 2158. Notice it's a little bit yellow and redder. It's a young cluster, but we're seeing it at some distance away through more dust. And so the stars are undergoing what's called interstellar reddening. And I'd have to check this cluster to make sure that it's interstellar reddening and not just a cluster that is older, because sometimes you can get that as well, where you have older cluster members that will have a significant number of red stars that might have gone into the red giant phase as they've evolved. But we'd have to check those.
Yeah, I forget. I looked this up when we looked at it last time. It's, I want to say, was it 2158 is like 9,000 light years away, and you said M35 is like 2,700 light years away?
Yes.
So it's several times farther away anyway.
Yeah, indeed. Okay, we're going to stop it here at 9. That's all we need for a cluster like this. It's beautiful. And we're going to rename our object for the database. It's going to be M35, and it's going to say OC for Open Cluster. All right. And so when we save it now, it's going to be in its own directory up there called M35 OC. All right. And it'll save that, the astronomical file format, for the ones who want to get technical with it, and then save exactly as seen for people who just want the coolest photograph there is. And to see those photographs, again, SkyTourLive.org or SkyTourLive.com, and you scroll down and it'll say, take me to the cool pictures, and you can go see them. We also have a gallery of our work which you can buy prints of. We're in the process of changing that. We were previously using a company called Darkroom, but they changed their entire business model, making it almost ludicrous to try and sell your work up there if you want to actually make a profit for your organization. It's a ludicrous pay scale now. So we're going to do it differently, and that's the thing that Robin Curtis is helping us with, as you'll see. So we'll keep that under our hats for now. So there we go. So we saved it exactly as seen. So now we can get rid of the stack, and we can go back to our night vision mode here. And the night vision mode is going to allow us to see what's going on.
Mark, may I ask a question?
Yeah.
How many degrees above your north wall would you need to be able to see the comet?
I think we calculated. Let me go back here. I can show you directly when we come in here. Okay, first of all, let's get rid of the object ID here. Come here, you.
I'm looking on Stellarium right now. The comet is actually up by 9 o'clock tonight. It's above the horizon, but
yeah,
it's going to probably wouldn't be visible for the observatory until at least 1 a.m., which is going to be too late for us, I suspect.
Yeah, I think so.
Yeah. But it's actually up 9 o'clock at night now.
Yeah.
Above the horizon.
Okay. Damn it. I keep there's a delay right now because of the load on the Starlink systems out there.
Yeah.
So I'm getting a delay that I don't like, but it comes and goes. All right.
Comet's darn near circumpolar now.
Yeah. But it's very low right now for us.
Oh, yeah. Oh, well.
Yeah. Wow.
Soon, folks.
Yeah, we'll see that comet before long. We are definitely subject to some delays right now. Okay, we got it. No, we don't. Alrighty. That is just... That's a long delay. Sorry, we're going to wait this one out. Wait this out. We will wait this out. So if you have any questions, you might as well throw them in there now. Ronald's asking, is the delay from the satellite? Yes, it's from the Starlink satellites. I don't know why, but it is. Must be a lot of people on the Starlink network right now. We've had that happen too. All right.
Patricia, there were at least 2 big comets in the 90s. Patricia Slama. There was Comet Hyakutake in 1996 and Comet Hale-Bopp in 1997.
That's right.
And both were excellent comets.
Yeah.
But they both were quite different also. Hyakutake in 96 looked like a big blue-green spear flying across the sky. And Hale-Bopp in 97 was a big golden fan. Its dust tail with a nice sharp blue-green dust tail.
I remember that.
Or gas tail.
Yeah.
And it was huge. It was bigger than your hand in the sky.
All right, we're going to go check this out now. We're going to see if we can reach it. It's called the Rosette Nebula. So let's see. Oh, it looks like the telescope is gonna. It's still a little low for us. It's impinging on the wall, as you can see here. I mean, it's there, but it's close. Let me zoom us back out. It looks like we're getting some of our speed back now. Yeah. We'll have to wait just a little longer for this one.
Can you remind me where the Boogeyman is?
It's
That's between the Rosette and Orion, isn't it?
Yeah, I think it's. I'm gonna move this way.
Maybe we can try it sometime tonight.
Yeah, let's actually look it up. Oh, it's not known as Boogeyman. What's its NGC number?
Oh, give me a sec.
Excuse me. That was loud. I apologize.
LDN 1622.
Okay, that's right.
Lynn's Dark Nebula 1622.
Right. There it is. So let's see if we can go there. It looks... it's going to take us a little higher in the sky, so let's try it.
Michael, I'm not sure the answer to your question.
Okay, we're clear of the building with this one, I think. That haze we're seeing might be clouds, so we're going to check that out. So let's go here and do a acquisition. Look at that beautiful arc of the winter Milky Way right there. Let's see if these clouds have come in or if we've got more clouds over here now. Whoa. Yep, we have some high altitude clouds. Look at that.
Wow.
Yeah, that's a lot of clouds. That came out of nowhere. This has happened to us before. Tomorrow night is supposed to be a lot clearer, but I wanted to run tonight and see what we could get. But you know what? We're still having fun, so we'll keep going. We'll keep going. What?
I don't know. Carry on.
Yeah, I'm. Let's actually see if we can get to the Orion Nebula right now and catch it. I mean, we'll see a piece of it. Let's see if it's got any. See, we're moving away from the telescope's wall. So there it is. That's beautiful. There's the Orion Nebula here, and this is the Running Man. And even through clouds, we will see a beautiful nebula. So I'm going to take a picture of this for everybody. Okay, so let's go toward the east. This nebula is about 1,500 light years away from us. It is what's called a stellar nursery. It is giving birth to stars. And in the center of this nebula is 4 stars that are colloquially known as the trapezium because of the shape they carve out there. And that is an interesting location because it's the trapezium stars and the others surrounding the trapezium that are giving life to this nebula and illuminating it, causing it to glow. Again, it's an emission nebula. It's the Orion Nebula, Messier 42. And Messier 42 is a location where we have a mix of a molecular cloud called the Orion Molecular Cloud Complex, the OMCC. And the Orion Molecular Cloud Complex is composed of a lot of this dark nebula, which you can't really see right now. And that's fair, because we're not taking pictures. This is just a 1-second exposure up here that we're taking, right? And it's just a live shot, all right? and it's our live shot. Now, if we actually cut that down and allow you to look inside, we can zoom in and see the stars that make this up. And this is something that I want to show you. As we get closer, you'll see that there's those 4 stars in the middle now, called the trapezium stars. And if I bring the gain down, you'll be able to see those stars better. There you go. So there's the trapezium in there, those 4 stars, 1, 2, 3, 4. And these, again, this is a live view. So we're actually able to see the power source of this nebula. All right. So now that we've got that, all right, we can now go back to our augmented view here. And there is the Orion Nebula in all its glory. And as always, we have satellites traveling through the field right there. See it?
See Bill Murray eating the Milky Way, or the
Yeah. I'm glad I don't see it, because if I saw it, I will never unsee it. So, you see those red colors? Those red colors now are, in fact, the colors due to the ionized hydrogen. And then you have these blue wings out here. This is a very sharp definition. This is a cloud of oxygen atoms mixed in with this dark nebula. And this cloud of oxygen atoms has been doubly ionized by these hot stars and thus glows greenish blue. That's the traditional glow of doubly ionized oxygen. So we're zoomed in here. Let's actually do a photograph and stack it. And we're just gonna do a 12-second shot. The Orion Nebula can benefit from a lot more exposure, and we typically will. But I want to just show it to you now, and we'll stack it just to show you what we get. All right. So that's our previous one that's up there on the database. That's the M35 and 2158. And this will be the Orion Nebula at 12 seconds. Well, there. Now you can see that there's an awful lot of detail in there, and I haven't even started to process this for you yet. All right, so here we processed a little more. Okay, color correct. And if we zoom out, you can see how amazing it is that this oxygen ionization is there, right? And then if we drag it down, okay, you can see that we have the Running Man Nebula up here. And in between is some really weird darkness that's like, what is that? Well, we could kind of push that to kind of bring it out a little bit. You know, and you can kind of see now that really is a dark cloud in there. A dark cloud that is going to extends all the way out here and into here. And these are satellites that you see. But that's only a 25 or a 12-second exposure. What we're going to do is we're going to clear this, and we're going to do a 30-second exposure. All right? And a 30-second exposure is going to show you a host of different detail, and that's really cool. So let's do that. All right, we're going to get rid of the stack, and we're going to start it over. That's beautiful. Okay. And we'll clear what's in there. And now, after 30 seconds, we're going to see much more detail in that dark region between the Orion Nebula and the Running Man. You're going to see what's really there. And what's really there is my hot button as an astronomer. Okay? It is the location from whence life comes. All right? And you say, well, what's all that? Well, let's process it. A little bit of processing, right? Let's color correct. All right. And now let's start to bring some stuff out here. And we only have one stacked right now, but wait till we get to, yeah.
I'm sorry. Excuse me a moment, please.
Sure. So now you see this, and once we get to this next one, the detail will start to show up more as we get a better quality here. Look at that. Yeah, we're definitely approaching now a much more detailed view, right? Now, when we show detail like this, we unfortunately lose the softer and brighter detail in here. But we have a way of processing that to bring it back for you, so you'll see the soft detail in here and this detail. So you'll see it more like the human eye might see it. And that's actually some of the processing we do for the Patreon subscribers. So now, closing in, all right, on this guy, if we zoom in a little bit, you can see that the Running Man Nebula extends all the way out here. And then we have this detail in the cloud here. Just amazing. And some of the, again, this noise is going to get less and less and less as we get more stacked images. And it'll become much clearer. But this is just beautiful. And this was invisible. We couldn't see this before. But now we notice that nearly everything we see in this shot is surrounded by dust. And this is Orion, and it is the Orion molecular cloud. And that dark dust is composed of silica particles, and carbon atoms that have bonded, to each other and formed a bond to make carbon molecules. So you have carbon-carbon molecules. You have the silicon-based interstellar dust, and on the surface of all the dust, these other materials out there will alight or land on these dust particles, and they will congeal with them. They will melt temporarily and then freeze. And then what that gives us is a particle that has an icy coating. And the ice can be methanol, formaldehyde, carbon dioxide ice, water ice is very plentiful. So you see, and we have ammonia ices and also. So we see that these dark clouds are the progenitors for life. They have all the materials needed to form stars, because what's in these dark clouds are also hydrogen gas. As you can see, these stars are ionizing the hydrogen gas in red, which is mixed into all this dust. Okay. Out here, not so much, because it's a little further from the cloud. But you can see this beautiful, beautiful cloud. Let's do this. We're going to actually maximize this thing now, because I want to show you this. Okay, so now what we're going to do is pull this over and get rid of our telescope for a little bit and go full screen. Look at that. Now that is just beautiful. Wow. The Orion Molecular Cloud Complex, also known as M42, Messier 42. I won't bother you with that. We'll pull that out. Let's zoom in and check out some of these other details, like this over here. This thing right here. This is a pillar formed by the hot radiation from this star is eroding material. The material here is a little bit more dense, so it actually allows for the stuff in its lee side to survive. So this looks like a painting, doesn't it? It looks like a painting. Look at that. Looks like a painting. Now, we can do a little bit more processing by taking this guy and pulling it down a little bit. And it hides some of the dust, but it also allows you to see some of the other details, like complexities in here. Look at those complexities in the O3 region of the nebula. Wow. Isn't this just beautiful?
There might be some baby stars hidden inside that pillar over on the far left now.
There might be, and we also know that this stuff here is being pushed and prodded by the hot radiation from these stars that are in the middle here. And those stars are actually shaping this gas and dust. But you can clearly see, when we move it down, you can clearly see how this dust sits in front of this nebula and this nebula. You can see it in front here. Those aren't voids, by the way, out here. These are not voids. These are dark nebulae, molecular clouds. And when the stars form in those clouds, they light it up one way or another. Here, there's a magenta-looking nebula inside this blue nebula. Well, that magenta-looking nebula is actually this color. It's a hydrogen-2 cloud. It's a hydrogen-2 emission nebula. But it's being seen through a blue-lighted cloud by the stars that are scattering, the dust that's scattering the star's blue light. So when you look at something red through blue light, okay, through a blue cloud, it takes on a magenta hue. So that's what we see here. It's light adding rather than paint adding. Very different. Look at this. Wow. Wow. Look at all the detail out here. This is just beautiful. Let me see if we can pull out more detail at that end. And let's pull this down a little. And you see there's some more detail in there. A lot of oxygen, a lot of satellites. But look at that. Yeah. Well, this is near the celestial equator, and most of them are there. I am telling them, not you, of course, you know. Look at that. Wow. I mean, it's a stunning portrait of a stellar nursery. Wow, that's just something. Yeah, the Dean Bosador says, can't get over the Running Man definition. It's quite nice. It is really quite nice. You are absolutely right. Let me see if I can just give a little more contrast even so. Here we go. And you can see here, you can see the gaps in the brown dust leading to more dark nebulae behind. Isn't that cool? Not bad for looking through some light clouds tonight, huh? Not bad for light clouds. Look at that. What a portrait. That's just something. Wow. Let's bring the telescope back here. Get that over. All right. And let's dock our stack again. Outstanding. All right, I'm gonna name this. This is 19. We're gonna go to 20 stacked images here. This is M42, and it's an EN and an RN. It's an emission nebula, reflection nebula. The blue part here is the reflection nebula. And as Daryl points out, some of this dark nebulae now may very well have young protostars in it. And that's something that the James Webb Space Telescope would have to tell us.
Michael has a question for you.
Okay. Let's go check it out. What's Michael ask? Are there more nebulae in spiral or any particular galaxy? Or do galaxies have the same percentage? They do not have the same percentage. In fact, galaxies that are what we call elliptical galaxies, are just big elliptical blobs that are mostly stars. There's very little gas in those galaxies. But in the Andromeda Galaxy, when you look at measure 110, which is the elongated elliptical galaxy that's one of its satellite galaxies, you can see a little bit of dark nebula like this that's actually curling around in the nucleus. So it's actually really interesting to see that. But spiral galaxies tend to have the spiral arms in which the stars are born in the spiral arms. And the way spiral arms form is a whole night in itself, because the way we think they form and the way they might actually maintain their shape is a very interesting set of topics. For instance, I'll just give you one. A spiral arm in a galaxy, you think, well, the stars are rotating in there. They're all rotating around the galaxy in the spiral arm. And the answer is no, they're not actually. They're actually moving through the spiral arm. The spiral arms are held together by something totally different, and their shape is made by something different, a different process. Not the fact that there's stars nearby. Yes, that happens, because stars are formed there. But they move out of the spiral arms. But the spiral arms stay there. And they're made of gas and dust. So what are the spiral arms? The spiral arms are an oddity called a density wave. And you've all seen density waves. Every one of you here knows exactly what this is. You just may not know it by that name. It's a traffic jam. When you get on the highway, you go, oh no, beep, 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 beep. We all slow down and we go very slowly. Then we speed up and get out of it, right? But from the air, in a helicopter, you watch cars approach this knot of cars. And they slow down. And then they move through. So if you had a bright, hot pink car, the roof was hot pink, you'd see it approach, slow down, get into the middle of the cars, and then on the other side of it get out. But there's still a knot of cars there. They're not all the same cars, but they're new cars that have moved in and formed this knot of cars, and then they eventually move out. So they're not the same cars the whole time. They're changing all the time. And that's the same way with spiral arms in the galaxy. Different stars at all times. But they move out. I'm just stunned by this. Daryl, this is beautiful. Look at the Running Man. It's just so beautiful, standing alone there.
Yeah. I see Mr. Burns in M42 now instead of Bill Murray. When M42 is overexposed like that, and then M43 there.
Which is this?
Yeah, that makes Mr. Burns' nose. So I can use spacing the upper left.
Smithers, release the hounds. Okay, sir. Wonderful. So if we were to reduce this. There, so we bring this down. Now you see it like you might see it in a big telescope in an eyepiece. You might be able to see it sort of like this. But what you're missing is all this stuff. All this dust. And what I'm showing you is how this telescope shows us all the dynamic range that the camera has. You can actually go down to nothing or go all the way up to where you can see this dust. And when we go to process these images, that same availability is there waiting for us. It's the coolest thing.
Yeah, but looking by eye, I know we've said this before, the dynamic range of the human eye, especially coupled with a large telescope, it will let you see the faint stuff and still see the bright stuff.
I think when you were I mentioned that. I mentioned how we process these to show it as the human eye sees it, where you can see the interior of the nebula and see the faint clouds.
Yeah.
Yeah. Well, that's beautiful. Okay, we've taken we got the 29. We're going to go to 30 right now, and then we'll stop. And that's M42. Okay, so we're going to say right now, we're going to say pause, and we'll save it. And save exactly as seen.
So those satellites appear to be in equatorial orbits. Would you think they are necessarily geosynchronous, or whatever the term is, geostationary?
Well, geostationary satellites, we're only doing a 30-second shot. And for a geostationary satellite, a 30-second shot is not going to take us this far. You know, or when we look at the singular shots, okay, the line is about as long as this line to that star, about like that. That's too long for a geosynchronous satellite. We're following the stars, not the geosynchronous satellites. They're staying over one portion of the Earth, so they're going to leave a little dash. But they're very small, and they're 17th magnitude or so. So they're actually very dim. These are too bright for those, I think. Plus,
yes, but I mean, for each successive 30-second exposure, you know, that I noticed early on when you had just a few images stacked, that you could see dashes in between, and they look like they smoothed out now.
Yeah,
that since the telescope is following the nebula, not the satellites, that they would trail off to the side because they're staying put.
Yeah, they would. They do. But their dashes wouldn't be. Their dashes. See this. Let's say it stops here, from here to here. Okay, from here to here. This size right here, for 30 seconds, is not enough. I don't believe, to be a geosynchronous satellite. I think these guys and the other ones we see that end up coming through here, some of these I know for a fact are naval ranging satellites for the Navy, usually ones that travel in threes. But we can look, and have looked in SkyTour LiveStream, we have looked for geosynchronous satellites and been able to identify them. So maybe that's something to do, huh? That'd be kind of cool. Okay, I'm going to stop this one now because we already saved it. It's probably already up on the database. Go back to our 1 second shot here. There we go. And now, just right near this one, it's actually a little further north. So Orion is now fully visible to us. I guess we might as well, right? And we'll be able to look at the Rosette next, actually, after that. Well, let's go up to Alnitak and check out the Horsehead and the Flame. You want to do that? Sure. Why not? Okay, first things first. Let me get my computer back here. Alright, and now we come here and say, tell the telescope to go. And it's going to race up there, and you're going to see a nebula show up right away. Okay, this is Alnitak, right? The leftmost star in the belt of Orion. This is Alnilam, the next star, right? And what we're going to do is move the telescope to bring us down to the Horsehead Nebula. There's so much to see here. It's almost like you have a clear night, you just don't want to go to bed. You know? Okay, so we're going to head east a little bit now. Move the telescope east a little bit. There's one of your favorite stars right there. Right? Sigma Orionis, right?
What's illuminating the Horsehead?
That's right.
It's what's illuminating the background behind the Horsehead.
Yeah. The wall, yeah. All right, let's we're searching now for a guide star, And when it starts its guiding, it'll have all 0, 0.0.0.0, like you see. Then it starts to guide, and we'll let it stabilize, and then we can set up our shot and do a... Let's try a 40-second shot. All right, and here we go. We are stable now. I'm waiting for that to pop in. All right, now we can do our shot. And we'll go into the live stack here and clear this one. This was just a beautiful shot. That's probably up on the server already, guys. So again, SkyTourLive.com. Go to the really cool, take me to really cool photos, and you'll get to see all those. It looks three-dimensional because it is, okay? This thing here is sticking out in front of what's behind it. This stuff is in front of the nebula and the Running Man. It is just absolutely incredible. So I'm going to clear this now. And then when the sensor gets read out, we will get this right here. There we go. Oh, I didn't wait long enough. So I have to clear and wait for the next one to come in. I still had a slight motion in the right ascension, which is the east-west motion, left-right. And so we had a problem there. But we're guiding now. It says searching, so I think maybe the guider is having trouble locking on because it's on the other side of the scope and it might be impinging on the wall. I'm not sure. We'll find out. Let's see what we got. That's better. Alnitak is a bright O-type star. Most of its energy is being given off in the ultraviolet realm. But this is Sigma Orionis over here. There are a number of components to the Sigma Orionis system, all stars. And it is causing this hydrogen gas to be ionized and glow. Alnitak may be causing, I believe, the Flame Nebula, which is this really complex area here, to glow. And we're seeing this in 3D. So it looks like this is just right at the top of this wall. It's not exactly so. I mean, there's this is an edge right here to a giant molecular cloud, which is all throughout here. Okay, and it's all throughout here. Very, very complex area. Hey, Cindy Murphy.
Would it be fair to say, when you look at that, that Sigma Orionis is deeper in the field than the Horsehead is? It's lighting up what's behind it, yet it's not lighting up the Horsehead itself.
I'm not sure that's true, because when we zoom in on the top of the Horsehead, we do see a glow, a scattering glow that could actually be that, right?
Okay.
So it's possible. I don't know, though.
Well, you know what I mean? Like if we see the wall there, like we're seeing it edge on behind the Horsehead, and if it's being illuminated by Sigma there on the right, that it seems like Sigma would be farther back in the field than the Horsehead itself is.
Well, we actually should check that out and find out. There might be a way to do that. If see, first of all, guys, when you get distances in this product here, they aren't necessarily accurate. But let's take a look at. Let's see where Sigma Orionis, if it has a distance. It does. It says it's 1148.44 light years away. And okay, this is the H2 region, and it says the H2 region, it doesn't have a distance, and that's probably because it's it's in front, it's in back, it's three-dimensional. But how about Barnard?
Say the Horsehead itself, Barnard 33, I think.
Yeah, I want to try and see if I can. Let's look up Barnard 33, B33. Okay. And we don't get a distance for Barnard 33. No. Well, we would have to consult some studies, that's all.
Oh, I can look it up.
Yeah.
Give me a minute.
Obviously, we have some clouds that have come in here because we don't end up with... Well, maybe let's find out. Let's see if we can filter them out. Well, we got rid of some of them. Look at that. Oh, stunning, stunning, stunning.
Wiki says Sigma Orionis is 1,264 light years.
Okay.
And Horsehead 1,500.
Hmm.
So it says the Horsehead is farther away than Sigma is.
Well, if the Horsehead is made up mostly of dark dust, dark nebula, and the hydrogen has been powered away by Sigma's stellar winds, being the lightest element there is, then perhaps it's true that it has been exposed, and that Sigma might be pushing this wall back over time. There's all kinds of manner of possibility for that.
Yeah, well, as you said earlier too, though, I mean, it shows me an image of the Horsehead now that obviously the top is being illuminated.
You can see it is here.
Yeah. Oh, well.
Yeah. That's all right. It's very cool. Wow, guys, this is really cool. Hello, Renee Cruz. Nice to see you. Kathy Prentice's with us. Hey, Kathy. Michael Galea, how you doing? Good to see you. Yeah. And I really am very happy that you guys came out. Richard Spencer, hey there, how you doing? I'm glad that you're enjoying the photos, Richard. We are too. This is just a really cool. OG Skywatch is here. How you doing, man? Good to see you as well. And I'm sorry if I missed anybody, but boy oh boy, it's really just a gorgeous night. Really gorgeous. Okay. Look at this. Even with light clouds, look what we got. I like being able to cut through the clouds, Daryl, I mean, I like that a lot. Gives us the opportunity to showcase what's going on here.
Yeah. Better not seeing anything at all.
Oh, there we go. So that's this whole region. So this is Alnatak. Alnalam is just out of the shot up here. That's the second star. So this is how much stuff is in the belt of Orion, and it's not even scratching the surface. There's so much more. So much more.
Still, can you zoom in on the Horsehead?
Yeah. I'm telling it to go, but we're subject to our little delay. Gotta give it a moment.
Yeah. I was wondering, still looking at the Horsehead and seeing where it's like the top of the horse's head is being illuminated somewhat.
Yeah, it is. As is the snout.
Almost like it's, You know, if you turn the whole image 90 degrees counterclockwise, so the Horsehead was standing straight up, and Sigma was directly above it, it's almost like it's directly above it, or you know, directly to the west of it. I guess as we're seeing it here.
There's the line. Yep.
So you know, it's shining directly down on the top of the Horsehead.
Yeah.
Like they're about, you know, the same distance away from us.
Kathy Pernisek says that's my favorite nebula. She says, I think that's my favorite nebula. That's very cool. I think that what's interesting is I've watched how we've grown in capability, guys. There was a time when the little tiny stars in the Horsehead Nebula would be elusive. We wouldn't catch them. But now, you look right here in the back end of the Horsehead, there's a star right in here. Can't miss it. There's a star right there. You can't miss it. There's a star in the snout. Can't miss it. We now have the capability to do so much more that I literally, I could easily be convinced not to go to bed and just stay up. And I've done it. Look at this.
That reminds me, are you doing that bending thing tonight?
I am not. I chose not to. I started to explore it early before coming in, and I didn't see a bang for the buck, so to speak, in doing binning. I could be wrong about it, but there's certain conditions where you should do it and certain conditions where you shouldn't. And I think for my objects that we're looking at tonight, I think that we don't need binning.
It might be something to experiment with first.
Yeah, agreed.
Okay.
Wow. All right, so this will be 16 exposures. All right, we're going to pause it. Actually, I'll let it keep going while I fill in the name here. All right, this is called Barnard 33, otherwise known as the Horsehead Nebula. All right. And there we go. So now we can pause it. And I'll save it. Wow, what a... I don't know. I just get overjoyed when I see this stuff. I'm looking... Whenever I look in this space, whenever I look at these places, I look at where we come from. That's what I see. That's what I see. If you guys are... the other part of what I do, if you've never seen it, is if you ever see History Channel and the show called The Proof Is Out There, I'm on a lot of the episodes as a image and video analyst, and sometimes as an astronomer. But I will be in Los Angeles on March 2nd through 4th for Alien Con. A&E is bringing me out there to be on a panel and represent them with their other video analysts that they have. I don't know anything about it yet. But then a week later, I'll be in Roswell, New Mexico, speaking at UFO Expo, which is a conference run by my good friend Tom Reed. Tom Reed is the guy who has the only UFO sighting and event that has ever been recognized by a state. Officially. It is Massachusetts. Literally, coincidentally, right near Douglas Trumbull's studio. Now, Doug passed away a couple years ago, or a year ago, and Doug and I were very good friends, and he knew of this event, which is kind of interesting, so it's kind of cool. All right, so I'm going to do another save on this, and if it says I can't, that's correct, because I already did it, and that's fine. I like that it doesn't give me a choice. That's good. All right, so they are saved. They'll be up there. We're going to get out of this now and go to our next object. So we're going to go back to our night vision mode, And it's going to come in the form of going here. All right.
Mark, could you give Izabela and myself a simple explanation about binning pixels?
Sure. You can imagine that these sensors that are on the camera, these CMOS sensors, they're square what do you call them? Square bins, okay? Like you throw stuff in bins. Now, this particular sensor, if you look up here on the top, okay, this particular sensor, I'll have it come out and show you, is 4,144 bins across by 2,822 tall, right? Now, those are the pixels that are responsible. Each pixel will grab information. When you bin, all right, let's take this and go to binning level 2. Actually, I better not, because what it's going to do is it's going to complain and remove my flat field process, because we'll do it later. But what it does is it takes the one pixel and it combines it with the several others around it and makes one logical pixel out of it. And so that one logical pixel is capable of seeing much more detail. You get several times the amount of light on one pixel, one logical pixel, as you would on one singular pixel. And so binning is sometimes used for objects to be able to see the faint structures. The trouble is, you can imagine, the size of the image is cut in half when you go to twice the binning, because now you're taking all the pixels that go 41, 44 across, and you're just making them over 2,000. And it's just actually going to shrink them all down. So literally, as soon as you hit bin, the image comes into like this size, because it's cut down. But it has the trade-off that it has the ability to have each pixel see more data. So that's kind of a rough explanation of how binning works. You follow that, Daryl?
I think so.
Okay. Good.
Follow
Now,
that, Izabela.
good. Now tell me what the hell I just said. I'm just kidding. All right. So from this position, I would like to try to do what we did before. That is LDN 16.
22.
Yep. Because it's not far away from this. It's right there. So we're that close, so we got that kind of a good shot of that. So let's go back and tell our system to go here now. So you'll see us get the streak on. Here we go. Right in time with the music. Okay, what's hiding in the background here is a nebula that is colloquially known as the Boogeyman Nebula. You can kind of see it already here. It's a dark nebula, all right? But we have to actually... I'm going to just give us a 1 second shot in our quick picks, all right? And then in our exposure here, I'm going to give us an exposure that's something on the order. Let me just get rid of this first. All right. Instead of 1,000 milliseconds, which is 1 second, I'm going to take us to 45 seconds. All right. And off we go. And I didn't exactly wait for the guider to be stabilized, but it's a dark nebula, so the information is going to take a little longer to come in anyway. So we can get rid of our night vision mode and go into our live stack and get rid of the previous shot we had. Ah, stunning. Stunning, stunning. Okay. All right. And this is known as the Boogeyman Nebula. There it is. And we will be able to see it clearer in just a few minutes. It actually is represented pretty well tonight, Daryl. Let's do this. There's the dark nebula. You can see it.
Yeah.
All right. I think we can probably do it right from here. Rather, I don't want to move the telescope right now. I think this looks pretty good. Because the Boogeyman Nebula, this is the interesting part of that nebula anyway, but still.
Sam S. had a follow-up question on the binning.
Okay. What did he ask? Can you read the question?
Binning sounds like what they do with a very large array. Is that analogous?
Oh, okay. Yeah, I think that's probably a good analogy. It's a very similar, very similar thing. Yep. Very similar. Okay, so this is going to be
Is it a little washed out with high clouds, or just
it might be
hasn't stacked it up yet?
both of those things could be true. There's the Boogeyman Dark Nebula. Yep. All right, so let's go and see just how bad the sky is. This is the previous sky. All of our stars were washed out. We lost the Milky Way. Let's now go see if we've gotten any of this back. Hey, I told you we're still going to go for it, right? All right, let's see what we get. Hey, we got some back. We got some back.
Well, maybe save the Boogeyman for a clearer night and go on to the Rosette or something. A showpiece object might show up better.
I agree.
Okay.
Let's do this.
The Boogeyman is really striking, folks, when this shows up well.
Yeah, we can get it to show up well. Actually, we can also increase it like this, show what's really out there. So you can see what's hiding inside this whole region. There's a lot of stuff in here. All right, well, we will avoid the Boogeyman for tonight. We won't save this one. Not to worry, we shall come back. Promise. All right, so let's go to our 1 second shot. And night vision mode. And now let's go back to our main window. Back out a little bit. And let's go to a signature, our signature location, which is a beautiful, beautiful object. It's called the Rosette. This object we're going to now showcases many processes that the universe does in short order when you have a new young star system or cluster. And that's what is in here, is this cluster. This is the Rosette Nebula that you see here. And we will center it up. And I'll just bring up a centering guide. Okay. And then we're going to head to the east a little bit. All right. And we'll go just a touch north. There we go. And now we can get rid of our centering guides. Okay. So now, even with some light clouds, prepare to be amazed. So we're going to do another 40-second shot here. And we will get rid of... I'm going to wait for our stabilizing... get the stabilization here. Okay. The guider is having trouble tonight because of the light clouds, incidentally. That's why the guider's having issues. But, hey, we're not doing badly, are we? Are you guys enjoying it? I hope you are. Okay, we're stable with that. So we're going to pop out and go into our 40 seconds, go into our live stack, and we will remove the previous. The Boogeyman. I'm amazed we can see these dark nebulae even through the cloud cover. Yeah. That's pretty cool. We'll have the same capability with scope number 3. This is SkyTour West number 1. We're going to have SkyTour West number 2. And we'll have SkyTour East back in a building by the spring because it's behind me, and we're going to put it back in the building.
I heard lumber prices are finally coming down.
That's what's our main problem.
Yep.
I need lumber prices to come down so that we can actually build the building. You know, we got linear actuators to take the top off, and, you know, testing shows that it'll work. All right, let's get this first one done. 3 seconds, 7 seconds, okay, 5. Let's see. All right. Where is my image? I didn't see my image. Okay, the image did not show up. Why? Let me do this here. Yeah. It said stacked 0, so what happened? Let's find out. It says 1 now, so now we have an image. That's better. Holy! That's pretty cool. There's the Rosette, guys. Absolutely stunning view. Let's do a little processing on this. Let me color correct first. Now let's bring the rest of the data in again. Look at that. What we learned from the Rosette is something very interesting. This cluster in the middle is a young, hot cluster. It's only been around for several million years. And this cluster has already carved out a cavity around itself. See this? This is a cavity carved by those hot young stars. And what's happening is this is hydrogen gas being blown around by these stellar winds from these very, very young, hot stars. And these dark tendrils of dark nebulae are all throughout this region, all right? But this region here, where this cluster is being caused to glow by these hot young stars. And where you see dark nebulae, well, that's dark nebulae. That's this dust we talk about all the time. And this dust is what, will make us us. That's how that works. But the stars in the middle here are literally carving out this interior, and we'll show you when I zoom in here. Look at this cavity. All right, absolutely stunning. we'll just do this to kind of showcase that a little better. The stars have this supplemental glow that we see because of the light clouds. It actually kind of looks pretty. But if you look at these tendrils, look at this, how this moves. It's just amazing how that goes and how that moves. Yeah. All right, let's zoom back out. Go to auto. So there it is. That's the Rosette Nebula. And
Izabela, the Rosette is not a supernova remnant that I know of.
Yeah, it's not. It's a stellar nursery, and these stars were born there, and that's why this is glowing. That's why there's a cavity here. We see cavities in a lot of young clusters, where we have this type of situation where the stars wink on, basically inside all this gas and dust. They then ionize the gas, and they blow away the dust. And this is what ends up happening. They also push away the gas, too, as they're ionizing it, so it moves further and further away while it's ionized.
It's very similar to when we look at the lagoon or the Eagle Nebula, stuff like that.
Yeah, you're right.
Similar processes.
Yep.
Similar results.
Yeah. So let me look at where we are here.
I know Montecero sits right next to Orion.
Yeah, that's where we are.
Might the dust clouds around the Rosette also be part of the Orion molecular cloud?
I'm not sure, but I wouldn't put it past it, because this entire region is just one massive interacting set of phenomena. So it's possible. I don't know for sure.
Let me look.
Let's go back to this.
I guess the answer is no. The Rosette is over 5,000 light years away.
All right.
So that's several times as far away as if we said the Orion cloud is 1,500 light years away.
Well, that's a distance to like Alnitak and the Orion Nebula, and clearly the Orion Nebula is in the OMCC, the Orion Molecular Cloud Complex. So yeah. Let's put that out there so we know what it is.
So this is like on the order of 3 times farther away.
Okay. Wow, this is it is very, very incredible.
This is one of those objects that back when I did photography on film, it was easy to take a picture of, but it wasn't easy to see. All I had to do was point a camera up that direction, open the shutter, like in a piggyback, and it would show up in a 50-minute exposure on 400 film. But to see it through the eyepiece, you needed a filter.
Yeah.
Remember seeing it, like many other objects, it was particularly through a 13-inch telescope with a hydrogen beta filter.
I want to show you guys something in particular. If you look right here, okay, inside this box, you see that little dot right there and that little dot right there. These are areas where the dark dust also mixed with hydrogen gas, is contracting. And these self-gravitationally condensing blobs are known as globules, in particular Bok, B-O-K, Bok globules. I tell the story, Bart Bok was at my university when I was getting my astronomy degree as a visiting professor, and he taught some of the astronomy classes that I was in. And we talked about Bok globules and how they operate. And when there's enough mass for them to start contracting, then a bright, hot cluster like this is not going to be strong enough to blow that material away in general. So it'll survive. The rest of the stuff around it got blown away. In fact, you can see a little trail. Let me zoom in on this a little more if I can. And I'll do it in just a second. Let me do this. All right. So if we zoom in on this a little more, well, I'm trying to. It's taking a sweet old time. Okay. But here you can see this circuitous little snaky line going out behind this globule. And that is the trail of lighter stuff, I believe, that was blown away. And then we have this globule here, which has a little snaky line right next to it, too, of material that's either fed it at one point or is now being separated from it. But these two things, they just go totally unnoticed. But these are the places where life can eventually arise, and where planets can eventually be formed, and where stars will eventually be born. So it's just, it's an endless universe with endless mystery and incredibly endless wonder.
Izabela, supernovas don't create planetary nebulae. Planetaries come from sun-like stars when they get old, and they kind of puff off their outer layers as they turn into white dwarfs. Supernovas usually create supernova remnants, like the Veil or the Crab Nebula, and they're a very much more violent process. Would you say protostars create emission nebulae? You could say that, I suppose. That's the whole stellar nursery thing. That
well, protostars are created in the emission nebulae, or in the dark nebulae, and then when they wink on, they will start to ionize, and they might do a little of that ionization before they wink on, which in our SkyTour radio astronomy show we just did, we showed a protostar that the James Webb Telescope actually looked at, and this protostar was ionizing some of the material around it. So, good night, Michael. Great to have you. Thank you for coming. Hello, Sean. I said hello in the chat. I'll say that Sean Paris is in the house. Nice to see you, Sean. Thank you for coming. Make sure you subscribe and check us out. That. That's cool.
Planetary nebula formation is relatively gentle compared to supernova processes.
I would say so. In the end, in a supernova, the neutrinos do the job at the end of ripping the star asunder. In either case, we have objects that are still hot. Supernovae remnants are probably hotter than planetary nebulae by a little bit. But we're still talking about outer layers that are being ionized by a white dwarf in a planetary nebula situation. And white dwarfs are 50,000 Kelvin on their surface. That's pretty hot. The universe is good at heating things. All right. Just beautiful. Look at that. What a stunning nebula this is. Let's see where it wants to do the processing.
Excuse me just a moment, please.
Sure. Let's, for the remainder, let's do this. Excuse me. Okay. Now let's bring it up. Fill the screen with this. This is live astronomy, folks. This is happening right in front of your eyes. I'm going to take away the object name here because we know what it is now. The Rosette Nebula. There we are. You can see other details forming here. You see these incredible pillars. Here's one right here. Pillars are a foundational element that we see in a lot of clusters that have nebulosity associated with them. Look at this. All right, let me point it out to you here. So right here, this is a pillar. You see that pillar? Here's another one. Okay. Here is another one. And there's two right here that are kind of overlapping here. So these pillars, if you notice, they all seem to point toward these hot young stars. And the reason they do is because the hot young stars are responsible for these pillars. So when you have a dense material at the end of the pillar, say it's starting to gravitationally condense like the globules we saw up above, okay, then the hot stellar winds, the protons and electrons from this stellar wind and the ultraviolet energy is pushing on that material. But the denser stuff stays behind, and what it does is it protects the stuff behind it. So when we look at this, let's see if we can zoom in some more. Okay. When we look at something like this, all right, it's taking some time to zoom in, sorry. The hot material can't push this stuff away. All right. Oh, I see what it did. Sorry. Okay, now I can zoom in. Okay. So when we come in now, all right, you'll see this pillar. Now that we've stacked 22 of these, it's pretty obvious. So there's your pillar there, right? So this is the densest part of the pillar, and then these hot young stars are spraying this with ultraviolet energy and high energy protons and electrons, and it's pushing against this really hard. But what's behind it is protected. It's protected. It's like you standing behind a concrete column, you know, in a driving rainstorm. The rain will go around you. Maybe you get a little bit wet, okay, and but you will actually be protected from most of the rain. In the same way, this front end is like that concrete column. It protects what's behind it, and that's how these pillars operate. So this area around it got eroded away because it wasn't a dense area, and so we're in the process. Remember, we're seeing back in time, and we're also seeing in 3 dimensions. So as these stars are eroding this area around it, it's to this point in this cluster where it's gotten to this point where this part here is not eroded. This part has been all the way around here. See? So that is the story on pillars. And we see them, as Daryl pointed out earlier, we see them in Messier 16, which is the Eagle Nebula. We see them in the Lagoon Nebula. We see them in the Cave Nebula. We see them in NGC 7822. We see them in a lot of different locations in the universe. All right. That's just... I'll tell you, you saw the clouds. Even with clouds, it's stunning. I'm impressed. I'm impressed at how well we're performing. Okay, let me have my telescope back here. Come over here. There, thank you. And now at 25, I'm going to go into the live stack here. I will dock the stack back underneath. And I will wait for the 26th. There it is. 26. Pause it. And name it Rosette Nebula. There we go. And then we'll save the Rosette. There we are. It's saved. And we'll save exactly as seen. There we are. All right. Now, when you want to see exactly as seen, let me show you what I'm talking about. If I click on that, it brings up the Earthen view, a viewer that I'm using out there. You don't have to use the same viewer. This is what you get. And now what happens is you can zoom in into these images and move all around them and check out all the details in the images for your own. And there are those globules I told you about. All right. Okay, right there. And right there. And you can see the resolution of this is now a lot better because we stacked more. All that detail is preserved. Very cool. And that is in the... This is actually the low processed image. When you go to the higher processed image, it's going to even be better. All right. So that is that. And now we can stop the stack on this. Come back here and go into our night vision mode. There's the Rosette. Okay. And now we can go back and check out our screen here, our planetarium, and see what else we can see. Let's get rid of the selection on any of this. Okay.
Can anybody care to guess what the Monoceros is?
Monoceros. There you go.
Yep.
Thanks, Daryl. That was cool. All right.
It's like when I was a kid, Triceratops was one of my favorite dinosaurs, and that just means 3 horns. And Monoceros means 1 horn.
That's it. And now for a fun cluster. This is just plain fun.
No.
All right. Here it is. It'll come in here in just a sec. There it is right there. Can anyone see what this is? I'll zoom in a little. What does that look like to you guys? I know what it looks like to me, and I know what it looks like to Daryl. But what do you guys think it looks like?
I still remember the first time I ever saw this.
In a telescope?
Yeah.
Huh. Very interesting. Hey, Rascally Rabbit. James Dugan, hey there, how you doing? Sean Paris says, man, I love this stuff. Class is in session. Well, yeah, you know, you get the benefit of an astronomer, and you get the benefit of an astronomy popularizer. I call him the astronomer Daryl, and you get the benefit of seeing cool objects in the night sky, and learn about them. You know, and we always say, if you're not careful, you might learn something. You know, but thank you. That was very cool. Izabela says, why? Did I ask a question that required why?
Oh, it was on her list.
Oh, what, this particular cluster?
Yes.
Oh, it was, wasn't it? Oh, it was. Well, when we come back, Izabela, we'll take you on a tour of this cluster again, and you can certainly dictate what you would like to do with it. Right now, what I'll do is I will take a quick. I'll just take a little exposure of this. If it would let me click in here. So does anybody know what this is?
It's a star cluster.
Yeah. But to those looking at this, we're going to do a 25-second shot of this because it looks like a little jewel. It's so nice. And we are lagging again here.
I see your comments, Donald Kunder.
Oh, did Donald say something that we didn't respond to? Guessing from the angle Hercules cluster. Oh, okay, good try, but no. And when they tell you, you're gonna kick yourself. But let's do a 25-second shot first, and then we'll stack it. Let's also remove the rosette in our stack. Okay. Bring it back. Thank you. That's really pretty. Wow.
Yes, James. It's in Orion's right arm, left side as we see it.
Mm-hmm.
It'd be upside down, of course.
Maybe behind some clouds right now. Sure looks like it is.
Yeah.
Well, the best view of it that we got, guys, was actually, for tonight anyway, was looking at it dynamically at 1 second intervals. So we'll go back to that. And then I'll tell you. This is called the 37 cluster. Three, 7. It couldn't be more clear, huh? Couldn't be more clear. James Dugan says, "Can I see it in the southern hemisphere?" In its current location, boy, that's a good question. He might be able to see it, depending where you are.
Well, I'm sure he could.
Well, if he's down, like, if he's in southern Australia, then he's gonna have a different view of the horizon than northern Australia. Northern Australia will see more of Orion than the southern Australia. But because remember, it's upside down there.
Yeah.
All right. All right. Very good. Okay. Well, that's the 37 cluster. Clearly, we can't do much with it, unfortunately. I'm going to go back and do another shot of our AllSky camera to see what we've got here. Go to the AllSky. We're getting some significant lag tonight, which we don't usually get with Starlink. So I'm going to be talking to the Starlink people to see if something could be done. Okay. Now we're going to do one acquisition. Let's bring it down. See what we get.
Would have got a light turned on in their yard?
You mean here?
Yeah.
Actually, that's a security camera on the gun range. There's a gun range in the on the property, which is a lot of fun. We get frustrated in the building and then just want to go shooting, you know.
Nice. Sounds like my kind of landlord.
Yeah, well, they're good people. Yep. Okay. So the skies are kind of getting worse for us right now. But let's see if we can check out one more thing. And the lag is getting somewhat unbearable too. See, that's going to go away now because I clicked it twice. See? Alright, we're going to be speaking with Starlink as well. I shouldn't have to have like a 10-second delay waiting for something to happen. See? Alright.
See you, rabbit.
Rascally's heading out.
All
right.
Hockey game just started.
Oh.
Rodney Dangerfield said, I went to the fight the other night and the hockey game broke out.
That's funny. Okay. I wonder. That's where we are. Yeah, okay, so I have to also I'm gonna hide the equatorial lines, bring up the zenith lines, because that helps us. So we should be able to see down here now. Well, wait, let me see. Oh, maybe not quite. We can try. I'll try this. We may not be able to see it yet. It might be a little bit low, but we'll try. See where the telescope's aiming? It's aiming along the roof line. May be clear of the roof line. But it looks like we may end up still having significant cloud issues. Alright, let's do this.
What were you going for?
The Seagull, which is right near it.
Oh.
Right near it, yeah.
I saw a really nice pic of the Seagull just a day or two ago. I don't remember where I saw it at.
You know, Izabela, I think this is also on your list, isn't it? Let's try something here. All right. Well, we're getting too much of a delay here. It's missing keystrokes. Wow, I did that a minute ago. All right. Jeez.
You're in trouble.
What do you mean?
Oh, Izabela's. If you were married, you'd be sleeping in the bathtub tonight. Let me put it that way.
Oh, Izabela, you don't have to change objects. I mean, the bottom line is that it's a cloudy night. We can't see these in any kind of beautiful way. Besides, there's only so many objects to check to pick from. You know?
And they'll still be there next time around.
Well, next time around it'll be like, maybe tomorrow night. Izabela, I also asked you, send me a definitive list of everything you want to see. And then we are going to focus on taking exposures that you want to take at the length you want to take. Like we can do a minute or 2 minute shots of some of these things for you if you want. And right now we're only going to do like 40-second shots, so it's not going to be as many seconds. So let's see. Let's try this here. Let's see what we get. I'm going to drop us down a little bit too. Okay, that's the upper wing is about there. This is the Seagull. Okay, there you can see the head. And I think, Izabela, you're interested in this area as well. And again, tonight is just object to entreat people to view them and enjoy. And we'll do a serious set of photos of them for you. All right. See how many clouds were with a 37 cluster? These clouds don't just go away. We may have those over the Seagull right now, too. But hey, this is a fun night. You see James' comment? James Dugan's comment?
I do.
Okay. All right, let's see if there's any data in here. Well, there's some data.
Ooh, that's interesting.
Yeah, but it's certainly not looking like it should, because it's a exposure that is crippled by the clouds.
Yeah.
Yep. Beautiful dark nebula tendril right here. Wow. Very nice. Okay, this will be the last object because I have to go to bed because I have to be up early to talk to A&E tomorrow because we got to iron out the logistics of the trip to Los Angeles for Alien Con.
Nanu.
Yeah, I didn't realize that Alien Con was their conference. But A&E is responsible for a great deal of it, if not the whole conference, as far as I saw. Pretty neat. And it's not just talking about aliens and dressed up as aliens. Sure, they have the cosplay stuff too. But what they also have is the science of extraterrestrial life, stuff like that. I'm going for video analysis, but I'm also an extraterrestrial life guy, so perhaps they'll have some opportunity there. Zoom in on this. There's the center of the seagull. If this is the eye, this is the really disgusting beak, and the lower beak, and the upper. I'm not sure where the seagull is in here. But look at this beautiful wispy structure here.
I thought from what I saw recently, if you back out, the long streak nebulosity is its wings, is it not?
Yeah. Yeah, this is the head, and this is the wings, so to speak, from what I understand. Well, let's see if we can coax a little extra detail out of the cloud base. Okay. All right, and then let's use a secondary histogram. Yeah, see, this shows you what else there is out here. Yeah, we don't use that now. We will use it later. Izabela says the Zigzag Nebula, she's talking about this right here, reminds her of the Chinese Dragon Nebula near the lagoon, which you guys have seen if you've been with us for any period of time. And it does. It looks very similar. We've thanks to Robin Curtis in the chat, we now have a database of every observation that we've done over the last year and 2 months. And Daryl asked me earlier, how many Perseus clouds have we shot? And instead of going through the data, the data in the files and looking for all of the ones that had Perseus cloud in it, I just did a quick query on the database and came up with a bunch of dates. And he went to look at them. So it's really much nicer now. But there's a benefit to this. Let's suppose you want to see all the spots we did the seagull, right? And you do get the seagull in there, and you have all the different seagulls. Now what you can do is use a software called a blink comparator. And there's software available for free and for pay. And what you do is you take the images and you cycle them through, all right? And you look for differences. And so, for instance, let's say that there was a supernova that occurred in this cloud somewhere. How would you know there's a supernova? It's going to look like another star, right? How would you find it? The way you'd find it is by showing this image, and then the image with the supernova in it, and just flash them back and forth in front of your eyes. And by doing that, you'll see the difference. It'll jump right out at you. That's how Clyde Tombaugh found Pluto. All right? Well, we'll do it with a digital process where we'll have digital images and then blink those. So we with all this data in the database now, we have the ability to go through and hunt for objects in the universe that might have been elusive or yet missed, like a galaxy with a supernova in it. Not everyone's looking at galaxies out there. If we're looking at them and there's a supernova, well, we might catch it. And unless somebody goes and takes previous shots they took of it and compares them, they might not ever find it. So that's what's interesting. So it gives us the opportunity to do other forms of real astronomy.
That's how they look for asteroids, too.
Yeah, that's right. You look for that errant trail that wasn't there or shouldn't be there. Yeah. Wow. Hi, Seagull. So once again, this is the Seagull Nebula. Oh, look, it says Izabela's house under it. The Aliens Universe channel. Hello from Toronto. Hey, thanks for joining us.
Nanu, nanu.
Make sure you subscribe to us and hang out with us. We have, well, I guess, 400 or 500 streams up on YouTube over the last several years. And we look at astronomical objects and check them out and learn about them. Okay, I'm an astronomer. Daryl's, let's say, my co-host. You just heard him say Nenu Nenu. He's the astronomer's astronomer.
Oh, stop that.
Well, are you not?
I'm
You don't
just
like-
some old retired guy.
Okay.
I'll
With a
pour you
lot
to
of
death if you
astronomy
give me
knowledge.
Give me half a chance.
Well, that's why we don't give you half a chance.
Oh,
That's fine.
I would never call myself that.
Well, I call you that, and that's my judgment to make based on your contributions.
Okay.
There you go. See, he's got to take it, guys. He's got to take the compliment. We appreciate him, that's why.
Thank you.
You're welcome. So, yeah, Aliens Universe channel, AUC, this is our telescope control area. This is our telescope control system. This is the telescope out in the building 2,500 miles away from where I am. This is me in Connecticut, in New England. This is the Seagull Nebula that we're taking right now. That's the time and date. This is our stack. We're actually sandwiching them to make noise-free images. And then this is the camera control cluster over here and the focusing control as well. So we have everything that anyone would want, to try and generate a really cool image. We can actually maximize the size of our image and make it bigger on the screen so people can actually see it larger. But that's very cool. And so we can see the beautiful area. This it's actually getting, even with the clouds, even with light clouds. I mean, look at this detail here. That's pretty cool, Daryl.
Yep. Oh, like
Wow.
I said in chat, it reminds me of a parakeet for some reason.
It does, because of that little tuft up here, right? A little tuft in that the part of the beak right there might look like a parakeet, yeah. And if this is the eye, and you ignore the star, then it does look more like a potential parakeet with a mullet. It's kind of cool. Okay, we're going to go to 17 stacked on this. And hopefully it'll be clearer tomorrow. Alright, so we'll pause this now.
I'm
Give
amazed
it-
how well it's doing, given the clouds.
I know. I'm very, very pleased. Part of the reason is the filters we're using. There are no filters that can cut through clouds, but we are minimizing the light getting to us from the clouds because of the filters we're using. So part of it is that. So we have the Seagull Nebula up there. We're going to say save it now. Then save exactly as seen. And as I've said before, these images will be up on our server in 30 seconds. And you get to see them. This, SkyTourLive.com, that's our portal. Go there. Scroll down and it'll say take me to the cool images, and it'll take you to a directory and explain how to navigate the directories. in order to get to the images we've just taken tonight. So this has been wonderful, guys. Thank you so much for coming. Let me remove that ID there. We don't need that. And we've saved this now. And we shall now exit this stack. Go into our night vision mode, which is this guy right here. All right. All right, well, guys, I want to thank you for coming tonight. We are going to close down for the night. We are looking through a lot of clouds. And tomorrow, if it's clear, we might be able to do this again. Certainly over the weekend, probably again. We do this a lot, as you imagine. Okay. And tonight's stream has gone on for 3 hours. 2 hours, 58 minutes, and 7 seconds as we speak. So we're going to be done at the full 3 hours. Not bad at all, right? Not bad at all. So, I shall see you guys. And I know that... let me just find one more thing here. There we are. Okay. So I will look forward to seeing you guys again very, very soon. I hope that you guys have an excellent evening, and we will return. And so I wish you a good night. And you know that music. Music starts and stops SkyTour livestream.
Good night, everybody.
We'll see you later, guys. Have a good evening. Good night. Thank you for joining us.